Hello, my name is Tom Hartley. I'm a PhD student at Cardiff University, sponsored by BAE Systems and the EPSRC. Today I'd like to talk about a paper written with my supervisors, Kirill Sidorov, Christopher Willis and David Marshall, titled SWAG, Superpixels Weighted by Average Gradients for Explanations of CNNs. There are many ways to create visual explanations for CNNs. We split these into three broad categories. Gradient-based methods produce very fine explanations where every pixel is assigned a score. These have been described as difficult or unintuitive to interpret. Activation-based methods such as GradCam use the activation map from the final convolutional layer as a foundation to build upon. These are popular but are incredibly coarse. For example, using ResNet, the final activation layer is only 7 by 7. Having such a coarse explanation could lead to an explanation being misleading by inadvertently highlighting areas that are not important. Finally, perturbation-based methods such as LIME or RISE are able to vary the size of the regions used to perturb the model, but at a cost. The more regions that are introduced to assign a score to, the more perturbations are required to achieve accurate scores. So, how do we create an explanation that is neither too fine or too coarse and is computationally efficient to compute? To achieve this, we propose SWAG, Superpixels Weighted by Average Gradients. This is a simple method that combines gradients obtained by backpropagation and regions created using the slick superpixel method. We assign a value to each superpixel by taking the mean of the gradients that lie within that superpixel. We found that using an initial amount of 300 superpixels combined with guided backpropagation gave good results. Superpixels have been used in a number of other explanation methods such as LIME or X-ray. In each case, an off-the-shelf method is used that uses the color space in the image to determine the superpixel boundaries. But we asked ourselves, is there a way that we can create superpixels that better align to explainable regions? That is, if some region the model finds useful is split into different superpixels, is it beneficial to have it covered by a single superpixel instead? We propose two complementary techniques for creating superpixels that work alongside SWAG. We did this by incorporating the guided backpropagation gradients into the slick distance function, which is used to define how a superpixel is formed. By default, slick uses only the spatial distance and color space. We label our SWAG method that uses these simply as SWAG. This is the top equation. We can alter this to introduce the gradients as well to inform the superpixel boundaries. We call this SWAG I plus G. Finally, we propose SWAG G, which removes the image completely and uses only the spatial component and the gradients to create the superpixels. So here are some qualitative results showing SWAG with the three methods of creating superpixels alongside some common visualization methods. Here we see that our SWAG method produces explanations that are less coarse than GradCam and less noisier than other examples. So to measure the accuracy of the network, we used both the deletion AUC metric and remove and retrain. For both experiments, the pixels of an image are ranked based on an explanation and are iteratively removed from most important to least. For local accuracy, the softmax score is measured as an indicator of how this affects the model. For global accuracy, the model is retrained after every removal step, and the model accuracy is recorded. In both instances, we measure the AUC of the softmax, or accuracy, versus the percent of pixels removed. A low AUC suggests the explanation is able to better locate regions in the image important to the model. In both cases, SWAG was able to outperform the other methods tested. SWAG G performed better for local accuracy, but for global accuracy, the combination of the gradient and image proved beneficial. We also ran computational efficiency tests to see how our method compared. We found that ours was much faster than perturbation-based methods, and much closer to activation-based methods such as GradCam. The increase in time taken to compute our method is due to the overhead of having to create the superpixels and weight them. Finally, we note that our proposed superpixel method is applicable to other explanation methods. To demonstrate this, we used LIME but replaced the default superpixel technique with ours. We found that we were able to achieve a better local accuracy score without the need to add more superpixels, which in turn would have required further perturbations. Thank you for watching our presentation. We have proposed SWAG, a method for creating visual explanations of CNNs using superpixels. In addition, we have also proposed two complementary methods based upon incorporating the gradient into the superpixel creation process. Additional experiments and results on other datasets are presented in the paper. Thank you.